In this lesson, we'll be talking about plane curves and parametric equations. So equations such as this one, x equals t squared minus 2 and y equals 2t for t between -2 and 3, we're going to graph them by plugging in various values for t and obtaining x, y coordinates. And one advantage to this approach versus the normal sort of graph x, graph y approach is that t might be time, might tell you, say, like where the particle is in the plane at any given time. So let's just make a table, and this table will have 3 columns. It'll have a t column, and an x column, and a y column. And the t doesn't get graphed, but it does sort of determine what point comes out. And specifically here, our t is between -2 and 3. Let's start by inputting -2. When we input -2 into t squared minus 2, -2 squared is 4, 4 minus 2 is 2. When we input that into 2t, we get -4. So the first point that I have is 2, -4. Next, let's just plug in -1. Then x will be -1, and y will be -2. Oops, I graphed +1. -1, -2. There we go, that's better. Now if we input 0 for t, we get that x is -2 and y is 0. If we input 1 for t, we have that x is -1 and y is 2. If we input 2 for t, x is equal to 2 and y is equal to 4. And lastly, if we input 3 for t, x is equal to 7 and y is equal to 6. And in this case, I want you to tell me the direction in which the curve is traced. So it's traced in this direction. And it does actually stop at this point and stop at that point. So there's no arrows off the end because your domain is restricted between -2 and 3. Alright, sketch the curve given by x equals root t and y equals t minus 5. So in this case, we do have an implied domain that t is bigger than or equal to 0. T cannot be less than 0 because you cannot root negative numbers. So let's make our table again, t, x, y. So when t is 0, x is 0, and y is -5. Next, we'll use 1 because 1 roots well, so x is 1, and y is -4. And then if we input 2, 4 is the next number that works out nicely. X is 2, and y is -1. And the next number that inputs well for t will be 9, in which case x is 3, and y is 9 minus 5, or 4. I think you can get the idea that this curve is going that direction. So what curves are represented by the parametric equations below? How are these curves the same or different? So x is equal to cosine t as y is equal to sine t for t between 0 and 2 pi. So x, y. So if we input 0, cosine of 0 is 1, and sine of 0 is 0. Let's just input things that are easy. If we input pi over 2, cosine of pi over 2 is 0, and sine of pi over 2 is 1. If we input pi, cosine of pi is -1, sine of pi is 0. If we input 3 pi over 2, at that point in time cosine is 0, but sine is -1. And lastly, if we input 2 pi, the x is once again 1, and the y is once again 0. So what we have here is 0, 1. 1, 0 is the first point. 0, 1 is the second point. 0, -1. -1, 0, sorry. 0, -1, then back to 0, 0. So these curves parameterize one revolution of the circle. So we have a circle traced once counterclockwise. Now, what if instead I have cosine of 2t and sine of 2t? So let's make a table again, and let's see how this is different. So t, x, y. So if t is 0, cosine of 0 is still 1, sine of 0 is 0. But because we have 2t, now inputting pi quarters, cosine of 2 times pi quarters is pi halves, which is 0. Sine of 2 times pi quarters is pi halves, which gives us 1. And then when I input pi over 2, I'll get cosine of pi, which is -1, sine of pi, which is 0. When I input 3 pi over 4, I will have that cosine of 3 pi over 2, which is 0, sine of 3 pi over 2, which is -1. And then inputting pi, I get cosine of 2 pi, which is 1, sine of 2 pi, which is 0. And I still have one more sort of iteration of this cycle. This repeats once more. So I start off by graphing the point 1, 0, 1, 0, then 0, 1, then -1, 0, 0, -1. So I still have a circle of radius 1, but instead of going around it once, I actually go around it twice. So this is twice around in a counterclockwise fashion. A circle with r equals 1. So the overall graph is the same, but the fact that this curve is traced twice does make it a little bit different. Some of the curves we had in previous examples are things where it seems like something that you should have been able to recognize the regular equation for it. So what we're going to learn how to do here is how to eliminate the parameter and turn this back into a Cartesian equation, so normal y equals or x equals equation. You can do this more than one way, but pick the variable that's easiest to, or the equation where it's easiest to get t by itself. In that case, I think I'll just pick this one. X plus 5 will equal 3t. So x plus 5 divided by 3 equals t. And then this x plus 5 over 3 can be input for the t in the other equation. So y would equal 2 times x plus 5 over 3 plus 1, which is the same thing as 2x plus 10 all over 3 plus 1. So y is 2/3 x plus 10/3 plus 1, and 1 is 3/3, so we have 2/3 x plus 13/3. So that's one way to write it. You could also write this as 3y equals 2x plus 13. Lots of ways, but basically what this set of parametric equation represents is a line with y-intercept 13/3 and slope 2/3. So for this one, notice that we have implied that t must be bigger than or equal to 0 because x is equal to root t. So we have that, let's get the t by itself with the y. There are two different ways we could write this. So y minus 1 equals -t, so therefore t will equal 1 minus y. And inputting, and we have that we can input this 1 minus y for the t in the other equation, and we get x equals the square root of 1 minus y. That's one elimination. Or we could say that x squared equals t, and we'd have that y equals 1 minus x squared. Now the one tricky thing about this form is you have to restrict the domain because this is only part of the parabola. Because your t's are positive, that means that the x's that come out are positive. So this is only the right side of the parabola. So if t is bigger than 0, x must be bigger than or equal to 0 also. Alright, let's eliminate the parameter in this curve. X equals t squared minus 2 and y equals 5 minus 2t. So I think it's easiest to isolate t in this equation. Y minus 5 equals negative 2t. Therefore, t is equal to y minus 5 over negative 2. And so x will equal y minus 5 over negative 2, the quantity squared, minus 2, which you could write as 1/4 y minus 5 squared minus 2. So we have a sideways parabola. Now this restriction on t, saying t is between negative 3 and 4, so t equaling negative 3 implies that y is equal to 5 plus 6 or 11, and t equaling 4 implies that y is 5 minus 8 or negative 3. So the restrictions on my y is that y must be bigger than or equal to negative 3, but less than 11. And I obtained those by plugging these t's into the equation for y. And I chose to do restrictions on y because y is what we're inputting here. All right, eliminate the parameter here to find a Cartesian equation of the curve. So what you have to notice here is that e to the 2t is the same thing as e to the t squared, because those exponents multiply, giving you back 2t. And using that idea, you can take this x equation and get the e to the t by itself. So x plus 1 is equal to e to the t, and y is equal to e to the 2t, or e to the t squared. And inputting x plus 1 for e to the t, we'll have x plus 1 quantity squared. So this is a parabola shifted left 1, and you have to figure out which way is it traced. Oops, that's the next part. So sketch the curve and indicate with an arrow the direction which the curve is traced. So we know that we have a parabola, so y equals x plus 1 squared. So we know that's our parabola, we just don't know which direction it's traced. So make a table and plug in some values for t and see what's happening. So when you plug in, say 0, e to the 0 is 1, 1 minus 1 is 0, so 0, 1. So we start at this point when we have t equals 0. If t is equal to, say, 1, we'll have e minus 1 and then e squared. So e minus 1, e is about 2.7, so we have about 1.7 and then about 2.7 squared. So that means we're somewhere over here. So the curve is being traced in that direction. Sketch the curve represented by x equals 5 cosine theta, y equals 2 sine theta, for theta between 0 and 2 pi. So this time our parameter is theta, so we'll make a table with theta, x, and y. Alright, so when we input 0, alright, 5 cosine of 0. So cosine of 0 is 1, so we'll have 5 times 1 is 5. Sine of 0 is 0. Inputting next nice number will be pi over 2. Inputting pi over 2, cosine of pi over 2 is 0, but sine of pi over 2 is 1, so we'll have 1 times 2 is 2. Next, when we input pi, cosine of pi is negative 1, so the x is negative 5, sine of pi is 0, and then 3 pi over 2. When we input that, the cosine is 0, but the sine is -1, so -2. And finally 2 pi, and we input 2 pi, cosine 2 pi is 1, 5 is 5, 0. So we have the point 5, 0, 0, 2, 0, -5, 0, -2, and then back to 5, 0. So this, it's like it's tracing an ellipse with a center at the origin. Now there are many ways to parameterize curves, and we're going to find parametric equations using a representation that I tell you how to set the parameter. So first one is just to let x equals t. And if you do that, you can take and parameterize y by making y equal to 1 plus t squared. And so that will parameterize the parabola 1 plus x squared, which you can prove using elimination. Now another way is to use the slope at any given point. So remember the slope is found by using the derivative. So m will equal 2x, or solving for m, x equals m over 2. And then inputting that into my y equals 1 plus x squared to get the other equation, the y would equal 1 plus m over 2, the quantity squared, 1 plus m squared over 4. So there's the parameterization for the y, here's the parameterization for the x. And you can also prove using some kind of substitution technique that this also parameterizes the parabola. Now here's a parameterization of an ellipse, and let's actually prove that this is true. So take the first equation and let's solve it for cosine theta. X minus h is equal to a cosine of theta. Divide by a. X minus h over a is equal to cosine theta. And solve the other one for b. Y minus k is equal to b sine of theta. And y minus k over b is equal to sine theta. And you know that cosine squared theta plus sine squared theta equals 1. At least you should know that. If you don't know that, shame. And in for cosine goes x minus h over a, so x minus h over a, the quantity squared, plus y minus k over b, the quantity squared, equals 1, which you can simplify to x minus h squared over a squared, plus y minus k squared over b squared equals 1, which, if you recall, is the equation for an ellipse. Now use this to find a parameterized equation of an ellipse with vertices at 4, 7, and 4, -3, and foci at 4, 5, 4, -1. So it kind of helps me to sketch what this looks like. So vertices at 4, 7, so 4, 7, and 4, -3, and there are foci at 4, 5, and 4, -1. Okay, now first of all, the distance from the top to bottom is going to be 10. So I'll just call that distance a. So 2a is equal to 10. Therefore, a is equal to 5. And we also know that the c, which is half this distance, so 2c is equal to 6, therefore c is equal to 3. And using the formula for the foci, we have c squared equals a squared minus b squared. So 9 equals 25 minus b squared, which means that b has to equal 4. So if B is 4, A is 5, C is 3, an equation for this parabola, or this ellipse is, we also have to find the center, so the center there will be 4, halfway between 5 and -1 is going to be 2. So 4, 2 is the center. So the normal equation is x minus 4 squared over squared plus y minus 2 squared over 5 squared equals 1, or x equals, so h is the 4 plus 4 from the denominator, cosine theta, and then y is equal to 2 plus 5 sine theta. So the last example we're going to do is we're going to find the equation for a parameterization equation called a cycloid. And a cycloid is a curve that is found by taking a point on a circle and tracing out a curve as that circle spins. And as that circle spins, you're going to get a shape that looks like this. And so we're going to find a parameterization of that cycloid. And so what we start by doing is we are going to parameterize this using the angle of rotation of the circle. So suppose we have the center of the circle, well, we'll say that it's C. And just because I sort of drew it badly, that C should be somewhere more up there. And then the angle of rotation is the angle right in there. We'll call that angle in there theta. And we need equations to parameterize this. And we have the point P, where P is the point xy on the axis. So theta is the angle of rotation. Okay, so call the distance the circle's rolled, let's call that OT. So the length of OT, that must be equal to this, because the circle has rolled that far. So we'll call that the arc of PT. And because of the definition of what a radian is, if this is a circle of radius r and the angle we have there is theta, that's equal to r times theta. Alright, now what we want to do is figure out the x-coordinate of that point P and the y-coordinate of that point P. And the x-coordinate of that point P will be given by the length of OT minus the length of, we'll say, PT. And we already know that OT is r theta. Now PT, because this angle in there is theta, we know that this side, so call that x, so according to trigonometry we have that x over r is equal to sine of, because you have the opposite side from the angle is the x, the hypotenuse is r, so x over r is sine theta, therefore x equals r sine theta. So r theta minus r sine theta, that is the x-coordinate. And the y-coordinate is given by the length of, we'll say, TC minus the length of, this point is Q, call that QC. and the length of TC is just r. QC, once again, using some trigonometry, we just have the adjacent side, not the opposite side. So we'll have r cosine theta. So there's the parameterization for the cycloid. And one application of cycloids, or two applications, are the Tautochrome and Brachistochrone problems. So what this problem states is that no matter where P is placed on an inverted cycloid, so no matter where a point P is placed on an inverted cycloid, the time it takes, so no matter where P is placed on an inverted cycloid, it takes the same time to slide to the bottom. And this is used in making pendulum clocks. So if you have an inverted cycloid and a point P here and a point P down there, the time it takes the blue point to slide down to the bottom is the same as the time it takes the red point to slide down to the bottom. And we didn't prove that, but that is one consequence of one thing that a cycloid was used for. It's used to design pendulum clocks. The time it takes to do one full swing versus one little swing is actually the same. And the other problem was you try to find the curve on which a particle will slide in the shortest time. And, of course, under the influence of gravity, and among all possible curves, the cycloid is best. We haven't proven that, but that's just two problems that cycloids can be or used to solve.